Great, thank you.
Yeah, you might have to look it up there.
Oh,
No, you don't see it here.
that's fine.
See it up there.
That's fine. Okay, thank you. Okay, thank you very much. I have only a small fraction of my collaborators online on the screen there, so I apologize for that. On in red is a student who is here and has a poster, so I encourage you to check that out. So I got to cheat a little bit because yesterday I got to give a little bit of the introduction in the introduction to the hands-on session. And Jennifer Burt was very nice to precede this with this exact same movie on radial velocities. So just to remind you what I mean by astrometry, radial velocities means you're looking at the Doppler shifts. Astrometry means you forget about all those colors and you just look at the motion of the star in the plane of the sky. So in this case, you're looking at it almost edge on, which is conducive to radial velocities. Also works for astrometry. Here you're looking at it face on, so this would be pretty difficult with radial velocities, but this is the best case scenario for astrometry. You're trying to measure those periodic shifts in the position of the star's orbit around the system's mutual center of mass. And this has become possible thanks to the Gaia satellite. Astrometry has a long history. It has a long history even in the context of exoplanets, as I briefly said yesterday, but it's really coming into its own now. And in the sense, me speaking here at the demographic survey is a little bit premature because right now we don't have much, but I hope to give you a sense of why that is, what's to come, what really sets the sensitivity of this survey, and what we can do in the meantime, which is going to be a significant fraction of the hands-on activity based on astrometry. So at a broad level, you're looking at the changing position of a star. And I want to begin by telling you what the star does if it is on an inertial path. If nothing's tugging it and it's just going off in a straight line, as Newton's first law says. So in that case, it just goes across the sky, and that's what you see in the left. We call the motion proper motion, and you need 4 numbers to describe that. You need to know 2 numbers for a position where it starts, and then you need to know which direction and how fast it's going. So that makes 4. 2 for position, 2 for velocity. And then there's one more, which is called parallactic motion. That's from the motion of the Earth and the fact that our perspective changes. Just like if I move, then the position of somebody in the front row relative to something on the back wall will appear to shift a little bit. Same thing from the motion of the Earth around the sun. If you know where the star is in the sky, you know what form that takes, you just don't know how large the amplitude of that motion is. The amplitude of that motion is called the parallax. The closer the star is, the more it appears to move relative to distant background sources. Put them together and you get a sky path like the one on the right. So that's what an inertial sky path looks like. And you need 5 parameters to describe it. 2 positions, 2 proper motions, and 1 parallax. If the star is being tugged or if there's something else going on, that 5 parameter fit is not enough, and your data will not be perfectly described by that green curve or something like the green curve. You'll need something more. Okay. Back 10 years ago, predictions for Gaia were a whole lot of planets. At this point, we haven't seen that yet, okay? That's not to say Gaia is a failure, not in the slightest, and it's certainly not to say it's a failure for exoplanets, but I want to give you a sense of why it is that despite the 6,000 planets in a 5-year survey, we currently have, depending on exactly how you're counting, a handful. If you're talking confirmed ones that were first discovered astrometrically, it could be as low as 1. So why is that? And I'm going to try to break this talk down into 3 different parts. The first, why are these results slow to come out? How is the sensitivity going to change with time? What really sets Gaia's ability to discover exoplanets? A second, and the largest part of this, is going to be what we can do in the meantime, and that's kind of going to anticipate or lead into some of the things in the hands-on session. And finally, what should we expect in the near future? Unfortunately, this is going to have fewer plots, more of me talking at you. That's because we don't have very much in the way of actual data from Gaia that will look like future Gaia data releases. There's one time series that they've released from a black hole orbiting a star, but even that, I don't know how much it has to teach us. They're still working on the data processing, ironing out bugs that I'm sure will be improved when the data actually come out. So for the first part of that, I want to give you a sense of what sets Gaia's sensitivity. You may have seen, if you were looking closely in the previous talk, that there was this plot of all these exoplanets, and there were little lines drawn on it where the different techniques were sensitive. And there was a line labeled Gaia. Why does the line look as it did? Okay, another way of saying that. So I'm going to argue this using two different limiting cases, and I'm going to throw in Kepler's third law. Kepler's third law is that period squared is semi-major axis cubed. So if I have a short period and I have the star going like this pretty quickly, then how easy that is to detect depends upon the amplitude of that motion. So the size of the star's orbit is going to depend upon the semi-major axis, and it's going to depend upon how massive its companion is. The more massive, the more it moves. The larger the semi-major axis, the more it moves. And then I use Kepler's third law up there on the top to turn that separation, r, into a period to the 2/3. At long orbital periods, I don't cover that whole orbit, so I don't get to count the semi-major axis. I only measure a little bit of curvature. I'm measuring an acceleration. And so then I'm just going to go to Newton's law of gravity, gm over r squared, and that's going to set my sensitivity. And so then I end up, again, using Kepler's third law to turn a separation into a period, more or less. I get t to the minus 4/3. So I get two very different scalings for something close in and something far out. The blue there are some Monte Carlo simulations that I did that should be pretty much correct. And you can see in that there's this t to the 2/3 and t to the 4/3 that do a really good job of explaining what's going on. That little weirdness at 1 year is because there's some confusion with parallactic motion. It can blend in to something that looks a little bit like a planet. And they cross over at roughly the observing baseline where I cover that full orbit. So those are the two different scales. And now I want to tell you a little bit about how those change as I continue to observe, because our current Gaia data release is about a little less than 3 years. And those 6,000 planets were not promised, but they were hoped to be discovered after 5. Well, 5 is more than 3. What's the difference? And to get that, I need to give you some intuition about how our sensitivity scales with how long I'm observing. So here on the left, I have a bunch of points. And on the right, I have those same points, but then I've measured them for longer. So how much better can I do with the extra points on the right than with the points on the left? Twice as many points, I actually get √2 times as much signal to noise. So that's the simplest error scaling that you would usually see. Twice as many points. My precision goes as the number of points I get, or how long I've been looking, to the 1/2 power. I observe twice as long, I get √2 times as much. It's very different, though, if I have a trend. Notice how on the left, you can maybe see that it's a line. On the right, it's a lot easier. So it's not just that I had more points, it's that I spread those points out over a longer period of time. So here, to measure a trend, it's not t to the 1/2, it's t to the 3/2. So one of those powers of t is from spreading things out. So I win with a longer survey. And if I go to an acceleration, it's even more dramatic. You can't really tell on the left, I don't think, that that's a parabola. But on the right, you can, even though it's only twice as long. And so I scale not as t to the 1/2, not as t to the 3/2, but as t to the 5/2. So that's a big part of the reason why Gaia hasn't realized its promise yet. That's also a huge part of the reason why Gaia, a nominal 5-year mission, was extended until its fuel ran out, because of these scalings. So it was the exoplanet science case that was a core driver of the extension of Gaia's mission. Coming back here, how are these lines going to change as we continue to observe? Well, for that red one, that's where I get the whole signal. That's analogous to that twice the time, root 2 times the signal. So that red line is going to move up as I improve signal to noise. It's going to move up as t to the 1/2. So if I have twice the time, that line is going to move up root 2 times as much or something. But the one on the right, that t to the -4/3 line, that's going to move up like t to the 5/2. So if I have twice the time, that's going to move up by a factor of 5 or 6. And that sweet spot where I have my best detection is going to move to the right, to longer periods. So hopefully that gives you a little bit of intuition for why it is that Gaia's power for exoplanets has not yet been realized. Okay, so without that at this point, with just a handful of Gaia detections, I want to tell you a little bit about what we can do in the meantime before that flood of information comes out, before Gaia becomes, hopefully, once we understand the data in detail, hopefully becomes a demographics machine. And in the meantime, we're going to use another survey to complement it, Hipparcos, which measured these positions and proper motions a long time ago, actually probably 35 years ago now was when it was actually flying and collecting data, but about 30 years before Gaia. Okay, and that brings me to the second part of this topic. So, a little bit of a pop quiz here. How many proper motions are shown in this? I have a position and a motion from Hipparcos measured in the early 90s, and I have a position and a proper motion from Gaia measured in the mid-2010s. So I'll give you just a minute or a few seconds before flashing the answer. And the answer is 3, because you have those 2 arrows, but you also have a change in position, and that is some average velocity. So if you have 3 proper motions or 3 velocities across the sky, then you can ask, are they the same? If they're the same, taking out the parallactic motion, then I'm in that case of that star going in a straight line, that inertial motion. And if they're not the same, there's something else going on, something that maybe I can learn about a companion from. Okay, if there is a slow change in proper motion, that's just an acceleration. And without even referencing Kepler's laws directly, I can just reference Newton's laws of gravity, that an acceleration is gm over r squared. And so our intuition is going to be built from that. I'm not going to build any intuition from Keplerian orbits, although once we actually fit orbits, yes, we will use those equations, but all the intuition is going to be from Newton's law of gravity. It's going to give us what we need here. It's not quite right to put positions and motions on here, and so I do want you to keep in mind what these spacecraft are actually doing. Radial velocity is measuring a velocity. You're measuring a Doppler shift. We're not measuring a velocity, we're measuring positions. And when we say velocity, what we really mean is we measure a bunch of positions and we fit a line. And you can see that here, if Gaia measures a bunch of positions, and then it fits some kind of line to it. If you go and look up Gaia data right now, it will give you the slopes of those lines. It will not give you those individual measurements. Those individual measurements are promised, but they're promised in the next data release. Not yet. And as you go to a very short orbital period, then, I don't know if, does this work? Yes, it does. Okay. If I go to a very short orbital period here, then the Hipparcos or Gaia observations cover a lot of the orbit, and the connection between the velocity and what it's actually doing becomes more and more tenuous, becomes cleaner the longer the period is. Okay, one other thing I really want you to keep in mind here is that all of these surveys, all these methods have selection effects and sensitivity biases. Transits are very much more sensitive to close-in objects because the probability is higher. Radial velocities are much more sensitive to massive companions because, well, they give a larger tug. This method is more sensitive to massive companions. It's also much more sensitive to things close to Earth in a way that other surveys are not. So if you have a transit survey, you care about how many photons you're getting, but you're not directly dependent on how distant the source is. Here we have a direct geometric dependence because that same physical distance represents a larger angle if it's around a nearby star. The closer the star is to Earth, the more angle I have to see that same physical distance. So astrometry is very heavily biased toward nearby stars and companions to nearby stars. And for Hipparchus and Gaia, for now, I also need those periods to be long enough that I have a reasonable connection between the velocity and the actual orbit. So I'm going to need orbital periods that are at least a few years long. That's going to be relaxed once Gaia is released, although still Gaia is going to have its best sensitivity at intermediate periods. Not too short and not too long. There's going to be a bit of a Goldilocks there. Okay. Now, if I have all of those ingredients, which I do for some planets and brown dwarfs, then there's something remarkable that happens. If I just ask about Newton's law of gravity, it's gm over r squared. Radial velocity, if I can measure radial velocity, measures one component of that along the line of sight. Astrometry measures the other component of it. If I can also measure how far away those two objects are, because maybe I take a picture with my big fancy telescope, I get direct imaging. I wind up with those three equations where I've not even referenced Keplerian orbits. It's just Newton's law of gravity plus a little geometry. I can solve those jointly and get the mass. So in that radial velocity equation, the mass of the star was hiding. Here it's not. You can directly measure the mass of the companion. So this is an incredibly powerful technique in the cases where we can get it to work. Not demographics, unfortunately. And again, demographics will come later. But in the time being, this is a hugely powerful thing that astrometry enables. Okay, so what's the catch? The catch is basically that these data sets are complicated. You have to calibrate them, and you have to understand them very well to be able to play these games. And so that's something that I've spent a lot of time on. I will very briefly review it here. I don't want to get into details. If you want the details, you can read the papers. But it's going to form the basis of the hands-on session, the results of this. We have to ask ourselves, do the data behave as expected? And to do that, I'm going to set up what we call a null test. If you've dealt with data before, you've likely encountered null tests in some form or another. You're asking basically, if my data are good, they should have some property. Do they? And so we're asking that question here. Most stars should not be accelerating like crazy across the sky. And so for most of the stars, are the observed changes in proper motion small? And do my errors that I look up in the catalogs, do they accurately reflect that? I can take a difference, divide by an error, and ask, does it make a really nice bell curve? Which is what would that's what passing the null test would mean in this case. I do that, and the data do not pass. That nice bell curve that represents passing, that's the black line. And those distributions are not the same. They're broader. And so that's a sign that the errors are underestimated. And so I have work to do to make these data pass the null test and have uncertainties that are trustworthy. What I'm plotting here is the difference between the proper motions as measured by Hipparchus in the early 90s and those long-term position differences. If I do that and I just take all the errors at face value, then the bright stars really don't look like they passed the null test. The faint stars look better, but still not quite. And if I turn toward Gaia, same thing. This is the difference between the Gaia proper motion and those long-term proper motions. So work to do, and I'm not going to discuss the details here, except to say that I think that with a bit of work, a bit of, I'll call it massaging the data, adjusting uncertainties, recalibrating things, fitting for some offsets, you can largely fix these problems so that they are suitable for use in orbit fitting. One of the bigger things we have to do is figure out how to calibrate the errors. When you look up the uncertainties in these catalogs, it's very tempting to just take them at face value and say, well, that's the measurement error. For a lot of these catalogs, that's not meant to be the case. And I think that's true with radial velocities also. When you measure these formal uncertainties, they're meant to capture many sources of error, but not all sources of error. There are some sources of spacecraft calibration that are not going to be caught. And that's accepted, that's anticipated. And so we have to separately go to the data and try to figure out how large those actually are. It turns out that for Hipparcos, there were actually two reductions of the data, especially for the later reduction. The errors need to be much larger than were officially reported. For Gaia, we need to increase the uncertainties by something like 40% in order to pass that null test. If we do that, and we figure out which stars are actually going to anchor that null test, in this case, we can use the ones from the radial velocity surveys that are not accelerating. They're not accelerating this way, they're probably not accelerating that way. And so it gives us a really beautiful check to see if these uncertainties are correct. Then this is before calibration, and after calibration, it really looks like now we pass. And so these should be much more trustworthy. At the end, we get remarkable acceleration sensitivities. I put a unit up there, 5 microarc seconds per year squared. A microarc second is very, very small. So 5 microarc seconds, if you want it in radians, is something like 2 times 10 to the minus 11 radians. So you're looking at the width of an atom on the other side of the room, something like that. That's the kind of sensitivity that we can reach. It's just remarkable. And that gives us access to the same kinds of accelerations around nearby stars that you would see with a small radial velocity trend. And so with that, we have something that we can really run with. Okay. And the catalog with these changes in proper motion is what you'll be using in the hands-on activity. There's a similar one by Pierre Carvella that I also want to acknowledge. Couple notes of caution that I won't dwell on here, but when you're actually using these, it's important to keep in mind that they're not true velocities, that they really are things that are a little bit more complicated. And so you do have to be a little bit careful in some cases. Once you have proper motions and you have these changes in proper motions, the next thing that you can do is actually use it to fit orbits and measure masses. This is something that's only been possible for the last 5 years or so. But in those last 5 years, there are a number of orbit fitting codes that have come out, and we've been able to use astrometry to fit orbits and measure masses in a way that 10 years ago I never would have thought possible. So I'll show a couple of results from those once I get past a little bit of intuition in what we actually get from the radial velocity and from astrometry. When I measure that difference in proper motion, I measure that acceleration in the plane of the sky, there's a fundamental degeneracy. An acceleration, according to Newton, is mass over r squared. Now, I could have a large mass far away, or I could have a small mass close by. I don't know which it is. And so there's going to be that fundamental degeneracy here. You can break it if you have enough radial velocity observations. Otherwise, you need something else. And there's been a long history of work, this is only a very small snapshot of it, combining astrometry with radial velocities in order to be able to measure the true masses and orbits of these planets. To show you how much radial velocities can add to this, I'm first showing my constraints on how far away in projection the companion would be if I only know the acceleration of the plane of the sky. So all I have now is astrometry. And you see that mass proportional to r squared up there? That's where I don't know whether it's distant and massive or closer in and less massive. Where it turns over, that's where I start to get confused, where the survey isn't that long, and from that earlier slide, the relationship between the velocity measured and the actual orbital path becomes increasingly complicated. So In that case, what's this? In this direction, the relationship between the velocities and the orbit is complicated. Here, this is just the uncertainty between whether I'm seeing something massive and distant or less massive and close by. If I measure a radial velocity trend, I do a lot better. The fact that there's a long trend here immediately tells me that it's not a short period companion, so I can erase all of the probability over here. And I see a little bit of curvature in this, and that little bit of curvature in this trend does something to erase this bit of the orbit up there. If my radial velocity orbit closes, then it's better still, and then I've snapped down to a single point. I know pretty much everything. And so this is the best case scenario, where I have enough radial velocities to combine with astrometry to get basically everything. Okay, there's one more clue that has been used in recent years, and that is, again, something you'll explore in the hands-on session, that Gaia gives a goodness of fit metric. It gives you a number that tells you how well a 5-parameter inertial sky path fit the data. That number is called RUI. I don't know why they called it RUI. It stands for renormalized unit weight error. But it's a number that is about 1 if the fit is good, and is more than 1 if the fit is bad. Okay? You can think of it as a reduced chi-squared if you want. So that has the power where, in a case like that on the top left, you could imagine that for, there we go, that for this case, that's not going to look like a straight line for Gaia. The star is doing this little arc, this orbit. And so in that case, the RUI will be high. In this case on the lower right, well, that looks pretty much like a straight line. The RUI should be low. It should be close to 1. And so this extra bit of information can distinguish in a way that the astrometry alone cannot. And so Flavien Kiefer has this tool called PMEX to combine the astrometry difference in proper motion with this extra constraint to, in this case, rule out a massive close-in companion. And so he can use the Gaia measurements themselves to essentially erase this part of the parameter space, and you're left with this part on the right. This is data from a real star, and so in this case, the yellow dot shows where the companion actually lives, where it was actually imaged. This has started to lead to new discoveries. Here's a particularly nice example from JWST. It's Epsilon Indi b. So this is one of the closest stars to Earth. That's important because, remember, astrometry is much more sensitive to nearby stars. And so the fact that this star is less than 4 parsecs away made a huge difference. It makes the astrometric signal much easier to see. And when you're actually looking at it, it makes that angular separation in the sky larger. So it's the best case scenario for being nearby. And it's maybe the oldest planet that we've been able to image. This is a few billion years old. We only imaged it with JWST because we knew where to look. There were indications from both radial velocity and astrometry that there was a massive planet there. And indeed, in the mid-infrared with JWST, we found it. This shows you an example of what orbit fits might look like. In the top, you see a Keplerian orbit. You see those ellipses in projection. In the bottom left, you see the radial velocities. And then here, this is the astrometry. These orbits show how the velocity in the plane of the sky is changing in response to this companion. And you have these 2 measurements plus another one that isn't shown from this position difference. So you can, if you're wondering why all those points seem to lie on the same line, or why they're all so closely clustered together, it's because there's that other constraint that isn't shown in this particular plot, which is that those curves all have to integrate to the same value as measured by the position shift. Another example that is a significant part of the motivation for the hands-on session is this planet called AF-LAP-b, which is not quite as close. It's younger than the other system I just showed, and it's very low mass. It's only about 4 Jupiter masses. And it's on an almost circular orbit. So this one was again discovered in part because of the astrometry, because we could see that the star is being tugged across the sky, and so it prompted these 3 groups to look harder. If there had been no signal from astrometry, there were no Gaia, I'm sure that somebody would have found it eventually, but I'm equally sure it wouldn't have been 3 groups at the same time. To give you a sense of what kinds of planets this has something to say about, if you're familiar with direct imaging at all, and these are some of the greatest hits that I'm sure Eric Nielsen will put on his slides. These are our favorite phone numbers and planets on the left. And a lot of them have very highly significant changes in proper motion in astrometry. And that means we can measure masses. So beta Pic, we can measure masses of those companions. HRide 799, we can measure a mass of at least one of the 4 planets imaged around that. Likewise for the other ones. For the brown dwarf hosts, in some cases, these signal to noises can be absurdly high, 100 sigma or even more, and we can get masses that are good to 1%. So it depends a lot on how strong your signal is and really on how close to Earth the system is. There's that selection effect that's very different from other surveys, but this has huge power. And so in my last couple of minutes, I want to give a few words about what to expect in the future. At this point, there is one planet discovered astrometrically by Gaia and subsequently confirmed. This is definitely going to get more, a lot more in the next few years. How much? I don't know, but we're going to have a lot more of these kinds of things. And so we'll be able to begin to do demographics with them. And to return to this plot, just to remind you from earlier, that red curve, that's going to move up like t to the 1/2. That purple one's going to move up like t to the 5/2. So for these intermediate period orbits, we're going to get a lot more sensitive. Things like Jupiter on 5-10-year orbits, we're going to be able to start finding those around lots of stars when Gaia DR4 and DR5 come out. And so a few expectations that I have, your mileage may vary, but this is kind of what I have in my mind for DR4. We're going to find a lot more planets. How many, though? I don't know. The 6,000 that were hoped for in that first slide, that may turn out to be optimistic. It may be hundreds, it may be 6,000, it may be more. I don't know. To a significant degree, I think it will depend upon how well we can understand and calibrate the data. And so that's going to be a challenge for all of us. First and foremost, for the data analysis team that's working on it as we speak, but it's going to be a challenge for the whole community. It's going to be based on twice as much data as are available now, and so especially for the longer periods, it adds immense power. The peak sensitivity is going to be at orbital periods of a few years. Past that, we're going to fall off very, very quickly. If today you go to Gaia and you say, well, I have 3 years of data, you got any planets with periods of 6 years? You don't want to trust those, because if you only have half an orbit, if it doesn't close, those fits tend to be unreliable. So there's going to be that point of unreliability, but the peak where everything is as good as it can be is going to be at something like 5 years at the next data release. Short period sensitivities are not going to be as good. So if you want to use astrometry to measure the mass of that hot Jupiter, sorry, out of luck. The signal is just too small in amplitude. The little path that the star takes has a very, very small radius, and so it's very difficult to find that. So larger orbits are good up to the point where you cease to cover the whole orbit, and then you start to pay a very steep penalty. So it has this weird sensitivity function that's very different from any of the other techniques that we've discussed. My number one advice to anybody working with the future Gaia data release is going to be careful of the uncertainties. And I think the Gaia team would tell you the exact same thing, that there are going to be issues with the data at some level. I think the data are going to be extraordinary. They're going to be better, way better than anything we've seen before. But that doesn't mean they're going to be perfect. And so don't assume they are. If you need them to be good to a certain threshold, you might need to check that for yourself. I certainly will be doing my best. And factor of 1.5 to 2 in error underestimations, I think, are borne out by these references that we've seen so far and are likely to be true in the future. Although, again, time will tell. And so I think this is both good news and bad news for demographics. The good news is that there's a huge power. We're going to be able to get demographics around every star in the sky, subject to this bias for things that are nearby, but not subject to a bias for quiet things, this radial velocity effect, where if the star is active, it's hard to find. That doesn't really apply with astrometry. Our selection effects are pretty tame. So if we can understand the data well enough, the selection effects are going to be very well defined. And I think this is going to be a help give a definitive answer for the demographics of moderate period massive companions, Jupiters and Saturns, on 5 to 10 year orbits. Okay. And I will take questions. Thank you.
We have 10 minutes for questions. Again, early career scientists don't feel, please ask questions. Maybe I can start by asking, or please. You can start with this.
Hello.
No.
Thanks.
No.
Thanks. Great talk. So my question is, what fraction of current RV planets on longer orbits do you expect Gaia to break the M-SIN-I degeneracy?
Good. So I would encourage you to stop by and see An's poster. She has a paper submitted where within that paper, it's a couple dozen. There are other groups where they have some more. So if you're talking bona fide planets, not stars, not brown dwarfs, then I think the answer is there are a few dozen where currently today we can break that M-SIN-I degeneracy. With Gaia DR4, that number will go up a bit. Yes. Oh, yes, yes, yes. So the question was, how many radial velocity planets, planets where we've measured the orbit of the star in response to the planet with radial velocities, that has an uncertain, it has a degeneracy between the alignment of the system and the mass of the companion. You have massive and face on, low mass and edge on. So how many of those systems can astrometry break the degeneracy and give the answer? And so right now, few dozen. In the future with Gaia, the next data release, it will be more than that.
Just a quick follow-up question is that if Gaia cannot break the M-SIN-I degeneracy for these longer period planets, then what would be the what would be the dominating limiting factor?
So Gaia is going to struggle if a star is distant. If the star is far away from Earth, that's going to be trouble. If the planet is low mass and or short period, that's going to be trouble. So if you have a Saturn or a Neptune on a 50-day orbit, Gaia is never going to have anything to say about his Neptune on a 50-day orbit. Too short period, too low in mass, and the amplitude of the motion of the star is just too small for Gaia to see. So it's going to be a steep function of the period of the planet, the mass of the planet, and the proximity of the system to Earth.
Thank you.
Okay, next question here.
Hi, great talk, thanks. I was wondering for the longer period, like plus 5 year orbital period targets with the epoch astrometry in DR4, how useful is the extra Hipparcos baseline going to be?
Extremely. So for those very long period systems, those are the ones where you can make some of the strongest statements and do some of the best science today. To give you an example of something, it's a brown dwarf, it's not a planet. But Gliese 229b, the first brown dwarf discovered, is on a 180-year orbital period. And the difference in proper motion between Hipparcos and Gaia is more than 100 sigma. And so we can get a 1% mass measurement of that. It turns out that Gliese 229b is itself a binary, which was a surprise. but was very strongly suggested by the fact that we measured a surprisingly high mass for it. And so you can measure the mass of the system in all different ways, and it all checks out just beautifully. There's a recent paper by Jerry Schwann from Caltech and from Will Ballmer at Space Telescope, where they go through different aspects of this. And that's just a beautiful case of a long period, pretty high amplitude signal, and just gorgeous results. As you get to lower and lower masses, it becomes more difficult. But I think this one here is a pretty nice example. Here's one where it is a planet. It's been known about, suspected for quite a while, and it was imaged, and now we have a mass, a 10% mass, and an eccentricity. This is from the combination of Hipparcos and Gaia, and so that's what we can do now.
Thank you.
Okay, we have time for another. Is there something online before?
Yes, we do have an online question.
Okay,
It's okay to go online.
Online now and then.
Okay.
another question.
Do we only depend on non-Gaia data for RVs, or do the spectra taken by Gaia also have sufficient resolution to add usable RV data?
Oh, good. So Gaia does have radial velocities. They are individual radial velocities published for some systems for which there is a radial velocity signal. These are not precision radial velocities. So they are radial velocities from space. They're good, but their precision might be 100 meters per second, not 1 meter per second. So this is great if you want to find a black hole companion, a white dwarf companion, a stellar companion. If you have a really massive companion, this is beautiful. And so for stellar binaries, you're going to have a combination of astrometry, which given the mass of the companion is going to be comparably higher, correspondingly higher in signal to noise. And you're going to have radial velocity, so you can do amazing work with binary stars. But again, the RVs from Gaia are not precision RVs in the same sense that the previous talk was about precision RVs.
Okay, so one last question. Yeah, go ahead.
Hello, I'm Marie from Notre Dame, and I had some questions about those packages that you mentioned, like Orvera, Orbitize, and Octofitter. I've been working with Orvera and Octofitter for the past month or so to varying degrees of success.
Okay.
And I was just wondering if you had any insight on the relative strengths and weaknesses of all three of those.
Okay, so as the author of one of them, I will try to be as unbiased as I possibly can. So we wrote Orvara intending to be as computationally efficient as possible and to integrate this Hipparcos Gaia catalog as seamlessly as possible. I think we did pretty well on the efficiency. I think we did well on the integration. For Orbitize, I don't know as much about it. It should work comparably to Orvara. In some ways, it might be a little bit slower, and I'm not familiar with exactly how they do the forward modeling of Gaia. Octofitter has been under significant recent development, and it uses Hamiltonian Monte Carlo, which requires derivatives. There are tricks that you can do to use automatic differentiation within your code. It's the only one of these three that has it. And so it can be significantly faster, potentially by a couple orders of magnitude. And so over the intermediate to long term, my suspicion is that if Will Thompson continues to develop it and to add some of these other elements, then Octofitter may become the clear choice. At the moment, I don't know that I would have a clear recommendation of any of those, but looking forward, I think Octofitter is the one to watch because of the Hamiltonian Monte Carlo.
Thank you.
Okay, then we are at a lunch break, so let's thank team and all the speakers of this session.